Okay, so let's get started today. I am going to start by reviewing a couple of the after-class activities that I've assigned the last week or so because there's been some questions I've gotten about them, so I want to go over them, make sure we're kind of up on recursion, up on what's happening with trees. Then talk about the rotate function from lab 10 that is giving you some difficulties. I know it's Dr. Plank referred to it as lab A. Anyone know why he referred to it as lab A? Because it's hex, yep. But at any rate, we'll talk about that, and then we will talk about the insert and delete operations in AVLTrees. So, start off, actually also wanted to say that I have now organized the assignments into different groups on Canvas for the purposes of computing a grade. It turns out that just having them in modules is not enough. You also have to have separate assignment groups for them. So I've now got all the different assignments categorized according to midterm, lab participation. There still has to be a little work. I still have to. I'm going to be dropping 3 of the pre-class participation activities and probably 2 of the after-class participation activities. And I have to make sure that the lab is correct so that in effect 100 points is subtracted out. But I'll get that all worked out. The totals are pretty accurate right now. They're kind of like a running total. Gets updated based on additional assignments you turn in, but it gives you a good idea of where you are in the course right now. Okay, so first thing I wanted to go over was yesterday's quiz, and one of the questions on the quiz, which initially I had the wrong answer for because I was so focused on the answer should be Chuck that I forgot when I did something that I turned the right answer into Sue. So I'm going to go over both the corrected version, which after someone pointed it out, I corrected it. So most of you saw this corrected version of the problem. And then for those of you who solved the original version, I'll show you that too. So the question was that this tree is not a legitimate AVL tree. It's a legitimate binary search tree because it satisfies the binary search tree properties that at every node, all keys less than you are in your left subtree, all keys greater than you are in your right subtree. But it's got a violation of the AVL tree one. So starting from the leaf, I wanted you to tell me what was the first node that violated it. And in order to do that, you have to be able to calculate the height of each node because the AVL tree balance condition comes down to height. It says that it's an AVL tree if at every node the difference of the heights of the 2 subtrees is 1 or less. So if it's not going to be a valid AVL tree, it's either not going to be a valid binary search tree, but it is a valid binary search tree, or the height condition will be violated. So I told you the height condition is violated, so let's calculate the height. The height of every leaf is 0, and then the height of interior nodes are the 1 plus the maximum of the heights of the subtrees. So if we just compute the heights of everything here, heights of all leaves are 0, height of Chuck is 3, height of Amos is 4. We come up with that particular listing for the heights. Okay? So looking at this, we can see that the first time that any subtree or any node has a difference of 2 or more in the subtrees is right there. So we also have a difference of 2 or more where I've highlighted it in red, but that's not the first node on the way from the leaves to the root. that violates the condition. The first one that violates the condition is that one right there, and therefore the node that's doing the violation is Chuck. Okay, so that was the answer that I wanted to be correct. However, originally I did not have Zach. Zach wasn't here. And that leads to something where I wasn't careful enough and could also trip you up, especially on an exam. So now, again, we do our numbering. This is 0, this is 1, this is 2, this is 0, this is 3, 0, and 4. And it looks somewhat like before, where it looks like Chuck is probably the one that violates the condition, because it appears at first blush as though the Chuck is the first node where the difference is more than 2. But this is where you have to be careful about a gotcha. Okay? So here's the gotcha, which actually gotcha me. And that is that even though there's no leaf here, there is a height to an empty subtree, and that height is actually -1. When you have an empty subtree, we say that its height is -1. And so it turns out that you have to be, just like Sherlock Holmes was suspicious because the dog did not bark in the night, you have to be aware of the fact that even if a subtree is not there, it has an implied height. And in this case, the implied height is -1, which means that actually the first node at which the AVL tree condition is violated is actually at Sue, not at Chuck, because the height of Sue's 2 subtrees differ by more than 1. The height of Nancy is 1. The height of Sue's empty subtree is -1, which makes the difference 2. And therefore, the first height imbalance occurs at Sue and not Chuck. So originally, the correct answer was Sue and not Chuck. Okay? So questions about that? Because pretty much guarantee you a question like this will be on the midterm. Okay, and I'm going to come up with an after-class quiz today, and there'll be another question of this type on the after-class quiz. So if you don't understand it, speak now, because you will be speaking to it later. Okay. So, second thing that was catching some of you was back on the assignment where I asked you to implement a recursive version of tree find. So the recursive version of tree find, let's see if I can get this bigger. There we go. So the recursive version of finding a key in a binary tree is what you see here. So most of you got the base cases. So if the node was equal to the sentinel node, you had not found the key. You had fallen out of the tree and you returned null. And if the key you were searching for matched the key at the node you were currently visiting, you had found the key, so you returned the node's value. What gave some of you trouble was the recursive calls. So if the key was less than the key at the current node, you needed to go to the left, and you did that by calling recursive find helper on the root of the left subtree, which is your left child. And the same thing if it's in the right subtree, the key is in the right subtree, you need to call recursive find on the root of the right subtree, which is your right child. So this actually isn't what got many of you. What got many of you was many of you did this. You forgot your return statements. You just wrote else if the key is in the left subtree, call recursive find helper on the left subtree, else call recursive find helper on the right subtree. And you forgot to return the value. Okay? Because that value has to, in effect, be returned through all of the recursive calls. I also noticed this happening on some of the earlier things. I think recursive, height was also an issue like this. You often need to remember to return the value of your recursive call. And in this case, the C++ compiler didn't do you any favors. Okay, so actually I didn't try compiling this, but I'm guessing if I compile it, it's going to, yep, I get the wrong result, but it doesn't give me an error message, which it should. Does anyone know what the error message should be for here? I forgot my return statements. Really, I should be getting an error statement from the compiler. Right. Very good. So the return type for the function is void star. So the compiler expects me to return a void star. But since I am not returning anything here, I fall out of the if-else's and I get to this point right here in the function, after the else but before the end of the function. There should be a return statement there then, but there's also not a return statement at that location. So at some point, the compiler should step in and tell me that I have not returned something from this function. But it didn't. And therefore, you compiled correctly but got incorrect output and wondered what the heck was going on. What the heck was going on is that the C++ compiler helpfully, or in this case not so helpfully, stepped into the breach and inserted return null. That's not so hot. Why is returning null not so hot here? What's the interpretation given to null? Yes,
never found anything.
It never found anything. So no matter what, you're pretty much returning null out of this function. You're like, no, Brad, right here, I return the value. Yeah, if you're way down in the tree, okay, so my key, let's say my key is E, and so way down here, I find E. Okay, so I pass the value for E associated with E back to this recursive call, but now this recursive call says, I'm ignoring you. I'm going to return null, and it returns null back to here. And so null is what eventually comes out of my function. And main says, oh, that's a drag. The key wasn't found. And I will print that it was a failure, when in fact it wasn't. Okay? So you need to remember to put return statements for your recursive calls when those recursive functions are returning a value. So I needed my recursive calls there in order to make everything work properly. Okay, now I didn't need a return at the very end because I could never get to the very end of the function. All of the branches of the ifs returned some value, so I would never get that far. Can any of you think of another situation where the C++ compiler is apparently inserting a return statement because you are not. Most of you are actually relying on the C++ compiler to do this for you. Yes? Main, very good. Main returns an int. Most of you, including me, forget to put a return 0 at the end of our mains, and yet it compiles properly. And the reason is the C++ compiler is putting a return 0 statement in there for us. Now that's not a good habit to be getting into, because as you see here, it comes back to bite you. Okay, but the big thing, big lesson is if your recursive function returns a value, then be careful about putting return statements in front of your recursive calls, because you may well have to do it. Okay, because you may well have to do it. Okay, now if you're combining the results, that's probably less important, because you'll probably combine the results and then return whatever the combination is. But here you're just parroting back a result that has been computed by a recursive call that you made. And so you have to make sure that you pass that result up the tree. Okay? We good? Okay. So that brings us then to Lab 10, where the biggest issue in Lab 10 is you have to do a rotate operation. You have to actually implement the rotate operation. I've gotten some posts on Piazza that I understand conceptually how to do the rotate, but I'm a little unsure how to do it in code, which isn't uncommon. So first thing I want to do is, I've gotten a couple questions about, okay, if I'm at a node, like if I'm at this node, and I need to do a rotate about it, okay, do I do a left rotate or a right rotate? Okay, so that completely depends on whether you're a left child or a right child. Okay, and you might say, well, let's say that I'm a right child. There's still two possibilities here. I could either rotate the parent down so that the parent becomes a left node, or, well, let's actually make the parent. Let's say the parent is A and I am E. Or I could try to rotate the parent this way to the right and bring it down here. Okay, so I could either rotate the A down and put it here, or some of you think I might be able to make the rotate to the right and then put the A here. But only one of these two rotates is valid if we have a binary search tree. Which rotate is valid if we have a binary search tree? The one to the left. Why is the one to the right invalid? Because A is greater than E, and therefore this is no longer valid, because A cannot be the right child of E in a valid binary search tree. So in fact, when you do a rotate, there's only one legitimate direction you can do the rotate, because the other direction will result in an invalid binary search tree. And the direction of the rotate is completely determined by your parent. Okay, so if your parent, if you are the right child of your parent, you will make a left rotate as shown here. And if you are the right child, the left child of the parent, then the only valid rotate will be a right rotate. Now, second thing, the book and I use different terminology about rotate about. And I'm consistent with Dr. Planck's notes, but we're both inconsistent with the book. So my terminology holds, which is I say that the rotate in this case where I have A and E, I say that the rotate is about E. Okay? The book in the similar situation says that the rotate is about A. So try not to get confused about the differing interpretations. I view it as more natural to say the rotate is about E because, hey, if this was a axle on a car, the rotate, to me, the physics is the rotate is occurring about E. Now, you may disagree. That's fine, but I'm the instructor, so I get to set the ground rules. So I'm going to say that the rotation is about the node where the rotation is occurring, not about the parent, which is what the book talks about. Okay, so you need to do this rotation. Let's go to the more abstract case now. So there's two cases that you have, okay? One is that you are a left child. So here you are as a left child. So here's your parent, and here's you, and you're doing a rotate. So here is your subtree. So there's some things that are going to happen, okay? So the parent is going to swing down and become your right child. So it doesn't hurt to write out everything that you're going to do. So one thing that happens is that the parent becomes your right child. Okay, so in our list of things to do, parent becomes your right child. Okay, what else has to happen when I do this rotation? The right subtree has to move. Where does the right subtree have to move to? Should become parent's left because parent displaced your right subtree and your right subtree has to remain to the right of you. And in addition, it's going to have to be to the left of your parent, which is fine because your parent just orphaned you. Your parent, in effect, just gave you up. That's so sad. Okay? But your parent gave you up, so your parent's looking to adopt someone. The right subtree is a good adoption. So your parent adopts your right subtree or your right child. Okay, it becomes the parent's left child. Now, I'm not going to write this step down, but there's something important here. What do you think is going to happen if I actually literally do 1 first and 2 second without saving the right subtree? I'm going to lose the pointer to the right subtree, and when I try to make my right subtree be my parent's left child, who do you think is going to end up as my parent's left child? No, you are not. So you just made the parent your right subtree. Now you're going to try to make your right subtree be parent's left child. Your parent's going to become your parent's left child. Wow, that's pretty tricky. Pretty wrong. Okay? So this is kind of like swap. If you forget to save the right subtree, you might not come up with the right result. So this is a little bit like swap going on. So you need to remember to save your right subtree. Okay, I'm not going to put that in there. But wait, there's more. Now, ordinarily, there wouldn't be, actually there is more. Okay? So, your parent had a parent. Okay? I'm just going to draw it straight up right now. That is your grandparent. But in the rotation, as your parent comes down, I can't do this very well, but as your parent comes down, you rotate up and you become the child of your grandparent. Okay, so you're rotating in effect up and you become a child of your grandparent. So another thing that needs to happen is that you need to somehow make your grandparent point to you. Now that's going to, you have to figure out, was my parent a right or a left child? Okay, so a third step is you're going to have to figure out if your parent was a left or right child of its parent and make yourself become this child. Okay, which means, i.e., make grandparents left or right pointer point to you. So that's case 3. So these are just things you have to kind of be writing down as far as tasks that your code needs to do. Now, there's more because Dr. Planck also makes you keep track of your parent. So there are parent pointers or back pointers up the tree. So whose parents are changing in this particular rotate? So let's see. Some back there. Okay, you are changing, your parent changed, and who else? Right subtree. So there are 3 nodes who received new parents. So these 3 nodes, you must also adjust their parent lengths. So the last thing is you need to adjust the parent lengths for 1, you, 2, your parent, and 3, your right subtree. So these are all original. But those are the 4 tasks your code need to perform. Okay, actually there is a prior task. The prior task is you have to find the node, because the first thing, so rotate is not called with the node to rotate about. It's actually called with the key of the node to rotate about. So the first thing rotate needs to do is execute the find algorithm so that it finds the node that contains the key, and then it performs the rotation. But once you have found the node, these are the 4 tasks you need to perform. A word to the wise. I would name these nodes explicitly in your code. So I would have a variable called grandparent. I would have a variable called parent. I would have a variable called subtree. Now, this will be a little different if you were the right child rather than the left child. Then it'd be a slightly different rotation, and that's why I would probably name it subtree rather than right subtree, because sometimes you will be doing the opposite rotation. But at any rate, I would name each of the nodes that is going to be involved in this little play of ours. So this story. So this story involves the grandparent, the parent, you, and a subtree. I would have variables that point to each of those 4 nodes, because it will make your life a lot easier. Now, the final thing is that some of you were like, well, what happens if I don't have a parent? That's impossible. It's impossible for you not to have a parent as long as you have been running the code correctly. Why is it impossible for you not to have a parent? Even if you're the root, you're guaranteed to have a parent. Why? The Sentinel node. So this is yet again why Sentinel nodes are so valuable, because they save us from these icky special cases. Okay, Sentinel nodes are wonderful because they really prevent annoying special cases from happening. Okay, now, the final thing, you might raise an objection, which is, but wait a minute, you are making a correct claim that every node has a parent, but not every node has a grandparent, because the root doesn't have a grandparent. Got you, Dr. Van der Zanden. The root does not have a grandparent. And you are 100% correct about that. The root does not have a grandparent. We also cannot rotate the root. Okay? So you have a check to make sure that you don't rotate the root. Okay? It doesn't make sense to rotate the root. Okay? It's the root of the tree. Okay? What are you supposed to be rotating it about? There's nothing to rotate it about. If it's a binary search tree, pretend for a moment there's no Sentinel node, there's nothing you can rotate a root about. You can't rotate the root. Okay, you can't rotate the root. So you should check to make sure that you're not trying to rotate the root. What also can't you rotate? This is something else you need to check, because Dr. Planck might be generous in his grade script. Oh, wait a minute, not generous, and test this condition. So what else can't you rotate? Pardon? What? You can't rotate a Sentinel, but you're never going to actually be able to rotate a Sentinel. Actually, my code was a little bit on the... I was going to say, what if he gives you an empty tree? But if he gives you an empty tree, you won't find the key. So you can't rotate the Sentinel because he gives you a key. He doesn't give you a node. So if you can't find the key in the tree, you can't do any rotation. But I guess that's the other special case, is if he gives you a key that's not in the tree, you don't want to do any rotation. So that's the other special case. But then you can't rotate the root. So what that means, though, this implication is if I can't rotate the root, well, every other node in the tree has a grandparent. Every other node but the root, so every node but the root has a grandparent. When we use sentinel nodes. Now, the sentinel node may be the grandparent, but every node will have a grandparent. So in fact, there really is no special case to consider here. As long as we find a node that contains the key and it's not the root, we don't have to worry about any special case. So I know I've been getting some questions about, wow, I have so much to consider. No, you don't, because the sentinel node takes out all of the special cases. There are no special cases. And because you can't rotate the root, there really are no special cases. Every node has a parent. Every node has a grandparent that you're going to rotate. The only special thing is it a left child or is it a right child? That does matter because that determines the type of rotation. So questions? Yes.
So are you saying that sentinel parent would be null then, or
So
would it just not have a variable named parent at all?
The sentinel node doesn't really matter whether it has a parent or not, because you'll never access its parent pointer if you're doing this correctly. Okay, if you're doing it correctly, then at worst, here is your tree object, and it has a sentinel pointer. So it points to your sentinel node. Your sentinel node points to your first thing, which can't be rotated. So the first two children that could be rotated are down there. Okay? So you never modify the parent pointer of the grandparent. So the worst that the sentinel node can be is a grandparent, which I'll denote as GP. At the only way the sentinel node is going to participate is as a grandparent. And its parent node is not getting adjusted. Okay, we're adjusting this one's parent node, this one's parent node, and because it is a left child, we're adjusting its parent node of the right subtree. But under no circumstances do we ever care about the parent of the sentinel node. So I don't really care what you put in for the parent pointer of a sentinel node. It should never be accessed by your code. Ideally, it should be null. You're not looking convinced.
Let me rephrase my question.
Okay.
How do we check to make sure that it's not the root node?
So, okay. So if it is the root node, let's draw that situation. So here's our sentinel node, which now I'll put a big X. Okay? So if it's the root node, it will be the right child of the sentinel node. Okay? We have said specifically you should make the root node be the right node of the sentinel node. So the way to test is simply to say if node, so let's say you have a pointer to node. Someone help me out. Going to be sentinel right. Okay, so if the node, if this is your pointer, if it's equal to, here's the sentinel, if it's equal to sentinel right, then it's the root. Okay, does that make sense?
Yeah.
Okay, so that's how you do the test. Yes?
I may just be thinking about this. Don't
Yes.
which technically makes the sentinel subtree. How do we get around that and relinking?
Okay, so the question is, what happens with a leaf node? So if we have a leaf node, so if we're down here at a leaf node, so here's a leaf node and it points to the sentinels. So we'll have this be like, I should be consistent. There's no reason why I'm making some squares and some circles. So let's say this is E and this is A. Okay, so now we are going to come down and we are going to, okay, so this is our, let's find a grandparent. So let's say that G is our grandparent. So I'm going to say GP. Please do not write GP in your code. I'm just abbreviating because I don't want to write out grandparent, but I want you to write out grandparent in your code. So this is parent, this is U, and in this case, which subtree is supposedly going to be adopted by our parent? Left or right? Okay, let's vote. How many think the left subtree is going to get adopted? Oh my gosh, you're in a minority. Okay, we're in Vegas. What odds should I give you on this? I'm going to give you a lot of odds because I'm collecting whatever bet you're making. So it's the right subtree, okay? So but we have to relink a sentinel node, it appears, okay? So in this case, we really don't, I did say I don't care what your sentinel node's parent becomes. So one thing that you can do is simply go ahead and make the sentinel point back up to, it's going to become the right child of E. I don't care, okay, because your find code never uses the sentinel's parent. Nothing in your code really ever looks at the parent node. So you're free to go ahead and modify the sentinel's parent, okay? Dr. Planck's code tried to make sure that did not happen. If you go and look at his delete code for binary search tree, he took special care to avoid making the sentinel's parent point anywhere. But in fact, since we never use the sentinel's parent, it really doesn't matter if we go and modify it. So actually, for simplicity's sake, I don't really care if you go ahead and naively set the sentinel node's pointer up to parent pointer to E, and later when you manipulate some other leaf, you'll again modify that sentinel. I don't care because the parent pointer just is never used. If the parent pointer was used, we'd have to be careful, but it's not. So if you want to go ahead and modify the sentinel node's parent, knock yourself out. Okay, no special case that way. Okay, other questions? Okay, we are good. I know. Well, you may be thinking, but it's a case of out of the, what do they say? Out of the pot? No, out of the skillet into the fire? Out of the pot? Out of the frying pan into the fire. So we now need to, so the rotation, the whole point of rotation is to help us, rebalance an AVL tree. So the thing is that we said that an AVL tree is a balanced tree. It's a balanced binary search tree. So the issue is that when we insert a new key into an AVL tree, or when we delete a key from an AVL tree, we may make it imbalanced, meaning we may violate the balance condition and turn it into an illegal AVL tree. So when we do an insert or a delete, we may need to rebalance the tree. And the way we rebalance the tree is we use a rotation. So that's why we've been focused on rotations. Now, you'll notice we haven't made a big deal about the find operation for an AVL tree. Why don't you think we've made a big deal about the find operation for an AVL tree? It's the same as the find algorithm for binary search tree. Okay, that's why we haven't said anything about the find algorithm for an AVL tree. Remember, an AVL tree is a binary search tree. It was on your quiz. Okay, an AVL tree is a binary search tree. It's just balanced. So we can do our find algorithm that we use for a binary search tree. It works equally well on an AVL tree. So an AVL tree is just a balanced binary search tree. So in fact, we'll say is a balanced. Okay? So for the same reason, what we do initially for inserts and deletes is the same as we would for a binary search tree. Okay, so the very first thing we do is that we insert, let's say here we have this AVL tree. The very first thing we do when we insert a mod right here is we insert it just like if it was a regular binary search tree. So a mod eventually ends up as the left child of baby Daisy. Okay? And now, when we do the insert, we need to recheck our AVL condition. And someone asked me actually on the quiz, was there ever a reason why we search from the leaves toward the root? And this is exactly the situation when we search from the leaf toward the root. It's why I actually made you do that question on the quiz. It's because when we do an insert or a delete, we start at the node that is inserted or deleted, and we work our way toward the root, and at each point we check to see whether we have violated the balance condition. Okay? So with a mod being inserted at the leaf becomes a height of 0. You can see here baby Daisy's height used to be 0. Now baby Daisy's height is 1. Okay, so that's no violation though of the AVL condition because baby Daisy's other right child is empty, which gives that a height of -1. So there's your difference, 0 and -1, we're okay. So now we have modified the height of baby Daisy, so we need to check whether Binky's height has changed. And Binky's height has not changed. See, Binky has the same height. If we reach a node that has the same height as it had before, we can stop. In order to make this claim that I can stop, I have to show that at this point the tree is guaranteed to be an AVL tree. And in order to do that, I have to show that every node from the inserted node up to the root is still the root of a legitimate AVL tree. So we have shown that Ahmad and baby Daisy are roots of valid AVL trees. If they weren't, we would have already rebalanced. So the fact that we have reached Binky means that we did not rebalance yet, and therefore the nodes below it were valid AVL nodes. In addition, anything that's not been modified, for example, the right subtree of Binky or the right subtree of Eunice, cannot have changed and therefore must still be a valid AVL tree. So now we have to prove that Binky, which is the node we're currently at, is a valid AVL tree. And we must show that every node above Binky on the way to the root is a valid AVL tree. So let's start with Binky. And specifically, let's assume that Binky's height used to be height h. And let's say that further, the two subtrees associated with Binky are, so here's Binky, and let's say its height is h, and that the two subtrees associated with Binky are A and B, and A is the changed subtree. Okay, so we know for a fact that before the change, A and B differed by height of no more than 1. So we know that before the change, A either had a height of h minus 2 or it had a height of h minus 1. We further know that since an insertion can only increase the size of a tree, that A's height cannot have decreased, so it's either the same, meaning it could still be h minus 2, or it could have increased to h minus 1, but it still must be one of those two values because the height of Binky is still height h. So since A is still constrained to be one of these two heights, it means that A, which is the changed subtree, still differs from the height of B by no more than 1. Therefore, Binky has to be meeting that AVL balance condition. So we've now shown that Binky must be a balanced AVL tree because it meets the balance condition. So the last thing we have to do is show that any nodes above Binky, such as Eunice, still meet the AVL condition. Well, since the height of Binky hasn't changed, and since that's going to mean no heights above Binky can change, and it's also going to mean that no heights in the unchanged portion of the tree can change. So if you don't have any heights changing above Binky, that means that all the nodes above Binky must still meet the AVL balance condition because they met the AVL balance condition before, no heights have changed, and therefore the balance conditions must still hold. Therefore, all nodes above Binky don't need to be checked because we know their balance conditions still hold. Therefore, we've shown that all nodes that matter to us meet the AVL condition. We've already looked at all the interesting nodes below Binky. They met the AVL condition because they didn't have to be rebalanced. Binky's height is the first node whose height hasn't changed, and we just showed why that means it must be balanced. And we've now shown that all nodes above Binky to the root, their heights cannot change, and therefore their balance conditions must still be legitimate. Therefore, the tree must be an AVL tree, and we don't have to proceed beyond Binky. We can stop the insert procedure at this point.
So I just have a question about how do you keep track of the height of your average?
Okay, so the question is, how do I keep track of the height? You have to add another instance variable to your BST node class. So you're going to have to explicitly keep track of this piece of information.
But when do you keep updating them?
During the insert function and during the delete function. So in the insert function, you are going to proceed initially as if you were inserting into a binary search tree. Okay, so in this case, we were inserting a mod into this. So we had this search tree right here. We inserted a mod, and the mod ends up as the left child of baby Daisy. Now we start making our way back toward the root. And as we make our way back toward the root, we update the heights of each node that we come in contact with. So we update the heights during the insert operation after we have inserted the new node. So it's kind of like 1, insert the new node, just like in a BST. Then 2, start checking and adjusting heights So start checking and adjusting heights, and if necessary, rebalance. Okay, so you're going to have to add some additional code after the insert that now starts making its way back toward the root, which it can do without recursion because we have parent pointers. So that's why Dr. Planck was keeping parent pointers. So you can use the parent pointers to start making your way back up the tree toward the root. And you will be checking and adjusting heights.
So like as I understand, you first you find where to insert that node.
Right.
And then when you find the location, you go like the way up to the root.
No, you put the node in there.
Yeah.
Just like, okay.
That's true. You put
Yes.
the node in there, and then you find all the nodes way up to the root. Like for every node that you visit way up to the root, you update the height.
Yes.
And then you check whether.
No, yes. As you get to a node, you check its height, and then
And then if it's not balanced, now you balance.
yes.
And then you keep doing way up for that.
Well, if the node's height doesn't change, you are done.
Oh, true.
Okay?
True. When you visit the last node on your way up to the root, when you find the height doesn't change, then that's where you stop.
Yes. So there's going to be 3 cases. Okay? We just looked at the first case. The node's height hasn't changed. Okay? So a mod, basically the first case says that when we insert it, we still are left with a balanced tree. That's the best possible case. Okay? So this was the simplest case where we were left with a balanced tree. Okay? Now, there may be situations. So here we're going to now insert, here's our tree, and we're going to insert Waluigi. Gosh, this is a tongue twister for me. Waluigi. Okay? So we insert Waluigi as we did before, and we again start with its height as 0, which means Luther's height, you can see, was 0. It now becomes 1. Okay, but the balance condition is not violated. Okay? Balance condition is not violated. So, because the empty tree's height is -1. So now we update Fred. Fred's height was 1. It now becomes 2. And you can see that Fred is highlighted in red. The reason Fred is highlighted in red is because Fred's left subtree is a -1. And its right subtree is a height of 1, so there's a difference in height of 2, which means that at Fred, we no longer have a balanced AVL tree. It is now imbalanced, and somehow we have to restore the condition. So we're going to have to rebalance. So now the question is, how do we rebalance? And the answer is, we will use rotations. Okay? So let's see what happens if we just do a rotation. And the first question is, what is the rotation going to be about? And I could let you do the different tries, but it turns out what we need to do is rotate about Luther. That is, we're going to take Fred and rotate it left about Luther so that it becomes a left child of Luther. Okay, so basically when you have an imbalance, the node at which the imbalance is detected is going to be taken for a ride. Okay, like on a Ferris wheel. So Fred ends up rotating down and becoming the left child of Luther. And what happens to Luther based on our rotations? Becomes Eunice's right child. Okay? And if we look at the new AVL tree, Fred has a height of 0, so Luther still has a height of 1. But now Luther and Binky are the two children of Eunice, and they differ by a height of at most 1. So it turns out we're again in balance. So by doing that rotation, we ended up balancing the tree again. So in fact, using this rotation, just that one rotation, we managed to rebalance the tree. And as we see up here, if the node's height, this was case 3, if the node's height has changed and it now violates the balance condition, you need to perform 1 or 2 rotations to fix the problem, and then you're done. So it turns out, I'm not going to prove it, but you could prove that once you have rebalanced just this one subtree located at Fred, the entire AVL tree is rebalanced, including whatever is above Fred. Now you might think, cool, this is pretty easy. And so far, it is pretty easy. Okay, so we managed to rebalance it. But let's make it a little more fun, shall we say. So, and let's not be this complicated about it. Let's start with something a little easier. So let's say we have Mary, and down here we have Ernie. So that's a balanced binary search tree. It is an AVL tree. Very trivial, but balanced. Now let's insert Larry. Okay. So let's now check our AVL condition. Height of Larry is 0. Height of Ernie is 1. Any imbalances at Ernie? Why not? Because its left, very good, its left child is empty, which makes its height -1. Larry's height is 0. Difference is 1, so there's no violation at Ernie. So Mary's height is 2. Any imbalance at Mary? Why, yes, because Mary's right child is -1. And her left child is 1, meaning the height difference is 2. So there is an imbalance at Mary. Okay, so based on what I just did, we might say, remember I said wherever the imbalance occurs, we take that node for a ride, meaning it's going to be rotated. So using what I did a moment ago, if I rotate Mary, how am I going to rotate her? How can I rotate? Okay, so I'm going to rotate Mary to the right. I'm going to rotate Mary down to the right. Okay? So Ernie gets a promotion. Congratulations, Ernie. You're now the root. Down comes Mary. What happens to Ernie's right child? Becomes the left child of Mary. This doesn't look promising. It just looks like we reversed the imbalance. And if we actually look at our heights, indeed, that was no good. Okay, so that single rotation didn't work so well. It turns out that if you are inserting quote on the outside of the tree, if you look here, way back at Fred, the insert of Waluigi occurred on the outside of the tree in some sense. Here, the insert in some sense came on the inside of the tree. Okay? Now, we will formalize that, but the problem here is still a problem. We haven't managed to get this thing rebalanced. And we call this a zigzag case because with Larry, we zigged. Here's the zig, and then we zagged. So we call it a zigzag case. And to fix an imbalance at Mary, we need a double rotation. Okay? So we're going to need to use two rotations. So to fix this, to fix the imbalance, requires two rotations. And we will rotate, it turns out, about Mary's grandchild. So to fix it, we're going to actually end up doing two rotations about Larry. So let's get rid of this original case because it was pretty unsuccessful. And we're instead going to try to do a double rotation about Larry. So rotation 1 is going to do what with Ernie? We're rotating about Larry. What happens when we rotate about Larry? Ernie becomes the left child. So here's Larry. Here's Ernie now, becoming the left child. And after the rotate, Larry rotates up and becomes a left child of Mary. Now that doesn't, we're still in balance, but I haven't violated my promise because that was just rotate 1. Now let's do rotation 2. And again, we're rotating about Larry. So when we rotate again about Larry, what happens? Mary comes down. So Larry gets another promotion. Mary becomes the right child. Ernie's the left child. And now, I think we'd all agree that's looking pretty balanced. Okay? So we're going to do two rotations. So to fix the imbalance requires two rotations about the grandchild. Now there's multiple grandchildren. It's going to be about the grandchild that we traversed as we made our way to this node. So it's the grandchild that was traversed. And you may wonder, gee, Brad, how come we know that we need to do two rotations about Larry? Well, it's not obvious. This was some mathematicians that were doing this, and they finally figured out that by doing rotations in this way, you could rebalance the tree. And in fact, AVL is for their initials, okay, which I meant to find out today but forgot to do. But there were, I believe, two of them. and I believe one of them has a double last name that came up with it. So their initials AVL is what it stands for. So they had to do their own experimentation. They finally figured out that there were two cases, what is called the zigzag case and the zigzag case. And they were able to mathematically prove that these were the only two possible cases. So I didn't tell you explicitly, but when I did the outside case with Fred, that was what we considered to be the zig-zig case, because the problem, if you looked at it, was two consecutive moves in the same direction. So we weren't going back and forth, but we went the same direction twice. So it turns out that there's only two possible ways that the imbalance can occur. One is with what we call the zig-zag case, and one is with what is called the zigzag case. With the zig-zag case, we can solve it with one rotation. And with the zigzag case, we can solve it with two rotations. With the zig-zag case, we rotate about the child of the imbalanced node. And this child will be the child we traversed. In the zigzag case, we do a double rotation about the grandchild of the imbalanced node. So in Lab 11, which you don't have to worry about until really Thursday, you will be implementing AVLTrees. Now on Thursday, I'm deliberately going slow, and it appears I've lost a day. There's no worry about that. I was pretty confident I would lose the day because this is a complicated subject. We will continue with this on Thursday. We'll finish talking about insertion, and we will go through deletion. Then next Tuesday, we will talk about B-trees, and we will finish up next Thursday with big O notation. So on Thursday, you don't need to worry about the participation activity because we won't get to it until Tuesday. Feel free to finish it if you want, but we won't get to it until Tuesday. We'll continue our discussion of AVLTrees on Thursday.
Professor?
1 second, just need to